So this is a joint work with Stav Ashur, my student. If you have any question, just stop, unmute, and ask it, because I'm not going to follow the chat. And since this is a scientific talk, let's start with a poem. Now, since this poem has nothing to do with the talk, I'm not going to read it to you, but I put a link to it in the chat, so you can read it while you zoom out from my talk. Okay, so usually when we speak about algorithm, we think in the framework of the regular input model, where we have an input, we read it, the algorithm computes something, and then hopefully it's output something. And in this talk, I want to advocate for a different model, which is the, let's call it the implicit input model, where the idea is that the input is given to you implicitly. Somehow you read it, somehow it's available to you, you don't read it, somehow it's available to you. Think about it as being stored maybe on a database or available through some library cores, and you have some input primitives that enable you to read some portion of the data, and you want to compute something, right? And so input primitives, you can think about it a little bit like geometric primitives, right? So if you implement computational geometry algorithms, it turns out that one of the main challenges is that you need to get the basic geometric computation correctly, and it's non-trivial, right? This was one of the nice things that Sigal does very well, is all those basic tests. So I want to think about it in the same way, right? That you have some basic input primitives. I'm going to refer to them as queries or oracle queries, and you want to compute something, and you want to do it with those oracle queries. And the main challenge would be to minimize computation time and the number of queries. And the motivation for this, well, reading the input sometimes is extremely expensive, right? Just think about big data, right? Just reading the data might be infeasible, almost infeasible, especially if you had to do it sequentially. And for most application in the real world, the input is already stored somehow, right? You very rarely read the input, right? You're usually building an algorithm within some bigger framework, and the data is already available, and you might already have this basic input primitives that can make things faster. And in the more philosophical level, the question is kind of what access to the data do we need, and what we can do with this access. And at some level, it's a mildly new way of thinking about algorithms, and the hope is to get something interesting on the way. So, so this implicit input model is, of course, very old, and there are hundreds, if not thousands, of papers on it. Maybe the most prominent place it appears is in convex optimization and linear programming, where you speak about a separation oracle. A lot of machine learning have this flavor of similar ideas. In particular, active learning is very much this kind of a primitive. There are also sublinear algorithms that to a large extent use similar approaches, and you can see it in a lot of other places. So this is really not a new idea, but I think that this meta problem is worth revisiting, because I think there are a lot of interesting problems in geometric settings that can benefit from this approach. And I'm going to show you a few examples. And those examples would be in the classification and clustering domain. So the first problem that we looked at is this undecided linear programming, or what I would call undecided LP, where you have a set of constraints, let's assume in 2 dimensions. So you have a linear constraint, but you don't know which way the inequality goes. So the way to think about it is that you just have a bunch of lines, and every line might be define either the constraint below, the area below the line, the half plane below the line, or the half plane above the line. Assume closed half space, but we don't know which one it is, right? And we want to find a feasible solution to this implicit LP. Now, of course, the most natural oracle in this case is the labeling oracle. You ask about this constraint. Is this constraint up or down? So of course, you can just ask all the constraints and do n queries if you have n constraints, and then solve it as an LP, but that's not very interesting. So let's look on a different model where we have a separation oracle. So I give you a query point, and the oracle returns me one constraint that violates, oops, what happened? One constraint that violates this this query, right? So either the oracle either says the point is feasible, at that point I'm done. If I have if the oracle says the point is feasible, then I know how all the constraints are decided, or which side of their 2 possibilities they chose, and I found a feasible point, so I'm done. But the more common situation is that I would return a constraint that says, no, this query point is not feasible because of this constraint. And when you get this separation constraint, you also get this its orientation. So you get a separation, and one constraint is being labeled in the process. Okay, so and now you can repeat this process, right? So now you ask about this new point, you get a new constraint is being violated, and you repeat this process until, let's say, now we have a point that is feasible, and we say, this is it. We found a feasible point. So the game ends when we find the feasible points. And the question is, how many separation oracle queries do we need to ask? Okay. Okay, so the naive implementation of the separation oracle is, of course, just scan the input, right? If you think about the LP explicitly, the constraint in fact are given to me explicitly, I could scan the input if this is a situation. And the reason I mentioned this, this is for the case where the LP is not an undecided LP, it's a regular LP, right? So I take an regular LP and I treat it as undecided LP. And if I had an algorithm that's polynomial in N and D for undecided LP, then since I can implement the oracle in linear time, I will get a linear time algorithm. Sorry, I will get a polynomial time algorithm in N and D for linear programming, which is unlikely, right? It's a big open problem. At least strongly polynomial is widely open. So on the other hand, you have to be careful about what you allow. So if, for example, I allow you the oracle query is not on the old set of constraints, but I'm allowed also to specify the subset of constraints I'm asking about, that it's not hard to show that you can implement, for example, Sariel LP algorithm in low dimensions and get linear running time. The constant, of course, in D is bad. So I'm going to kind of constrain myself to a situation where the oracle queries are on all the data. You cannot pick it on a subset. Now, this is sometimes called the counterexample model. It was studied in machine learning. It's also called Analguin equivalent query model for active learning. It's from the 87. And undecided LP, in fact, was studied before by Mas and Turan in the early and mid-90s. Okay, so first thing we did, we rediscovered the algorithm of Mas and Turan. And this performs the number of queries you have n constraint in the dimensions. And the number of queries you do is d squared log n, which is very good. But the running time is pretty awful, right? It's nd squared. Now we can slightly speed it up, but the number of queries deteriorate to being d cubed, but the running time is just n of d now. And we also have an algorithm that is much better. The running time is linear. The constant, of course, in d is not happy, but the number of queries is slightly worse. It's log d to the n. So that's essentially what we currently have. And we have special result for 2 and 3 dimensions. For 2 dimension, we can do log n queries, but you have to do a linear running time, but you have to do both labeling and separation queries. And in 3 dimension, we can do n to the 3½ with log n queries. And for other dimensions, we currently don't know much. Okay, so other problems that we studied in this model. So the other natural problem is separating red and blue points. I give you points. You don't know the colors. Maybe initially you know the color of a few of them. You want to find a line that separates the red from the blue. And the model here is that I give you a line. I say the Oracle queries give you a line and ask the Oracle, is this line separating the red from the blue? Excuse me. And if it is, then we are done. The Oracle would say you're done, but otherwise we will get a point that is mislabeled, right? So in this case, the Oracle might return us this point to say, no, this point is red and it's on the wrong side. Then we might ask this query, and the Oracle says, well, no, this is a blue point on the wrong side. And then we ask this line, and the Oracle would say, yes, this is it. This is the line separating it. So here it's more easier to understand why it's called the counter-example model, counter-example Oracle. If you think about it for a bit, you would realize that this is just the dual of the previous problem. So the same algorithms work. Okay. The fourth problem that we looked at was, I give you a set of points. Again, they are labeled by red and blue. So you can think about the task at hand to figure out for every point of the input what its label is. And the assumption is that there are k balls or k disks in the plane that cover the points, and all the points covered by the same disk have the same color. So those disks are monochromatic. And now the question, of course, is what is my Oracle query? So I allow you to, given a query point, I ask you for the closest point that is red and the closest point that is blue. And the task is to label correctly all the points. And yeah. So this is really a clustering problem if you think about it, right? You kind of want to cluster the point with disk, either this coloring constraints. Similarly, you can ask the same thing with monochromatic triangles, right? So you have point in the plane, and you want to label the point by red and blue. And now the Oracle queries I allow you is either, given a query triangle, is all the points covered by it having the same color? And if not, the Oracle returns a point that is not, that is in the triangle and is of the wrong color, right? So either the triangle is, all the points in it are the same color as I want, or there is a point colored in the wrong example, in the wrong color. Again, I'm assuming that there are k triangles covering the input, so I would like an algorithm that asks very few queries as a function of k. And you can also ask the same problem about terrain simplification. So I give you a set of points in the plane. every point has a height, and sorry, excuse me. So every point has an interval in the z-axis where it might lie. Think about it as the pointer really being sampled from some underlying terrain, and you would like to approximate this terrain by a simple terrain that have k triangles. So you want to find k triangles such that every point there is a triangle that passes the triangles are in 3 dimensions, and you want those k triangles to, if you want, stab all those vertical segments, right? Every point have a vertical segment associated with it, and you have to stab all those segments. And that's a problem that was studied before by Pankaj and other people. Okay, and what the Oracle query is? Well, the Oracle query is given a triangle in the plane, can all the points inside this triangle be approximated by, can be approximated by single triangle in 3D, namely, is there a 3D triangle that stab all the segments? If you think about it, this is an LP problem, so it can be solved in linear time once we are given the point in this triangle. And the other Oracle query that we want is, given a partial cover, give me a point, a random point uniformly that is not covered. Right? And what we can show is that you can find this cover, or if you want a terrain approximation with k log n triangles, and the number of queries is a function of k and polylog n, right? Which is and this also is the running time, right? So if k is small, we're getting a running time which is much smaller than the size of the input, which is kind of why this kind of result hopefully are interested. Interesting. In particular, those 2 Oracle queries, if I give you the input explicitly, those 2 queries can easily be implemented. They're essentially finding a uniform point that is not covered, essentially just scanning the input and collecting all the uncovered points and then uniformly picking one of them, and finding a triangle. If there is a triangle that can be approximated, this, as I said, is just a linear program. So that immediately yields an algorithm in the regular model with running time n times some noise in k and polylog. And this is quite interesting because all previous algorithms for this problem had running time which was quadratic in n. And this is very near linear, assuming, of course, that k is small. So hopefully that's interesting. Okay, so let me tell you a little bit more about this undecided LP and how to solve it. Unless there are questions before I jump in.
No questions.
Okay. Let me move on then. Okay, so we have a set of lines. I'm going to describe the algorithm in the plane and n lines, and we compute all their vertices, so quadratic number of vertices, and then we also put vertices on or in the middle of edges, in the middle of faces, right? So we have a witness point for every feature of this arrangement. So that can easily be done. And now what we do is we just treat all those points as just a set of points, and we forget about the lines. We take this set of points and we compute a center point for it. To remind you, a center point is a point such that every line that passes through it, well, passes through it is a bit challenging in my case. Let's try again. Okay, so every line that passes through it have at least a third of the point on each side, right? So a center point always exists, and in the plane it can be computed efficiently. So we take this center point and we ask the Oracle, is this center point feasible, right? If it's feasible, we are done. If it's not, the Oracle would return us a constraint that violates this center point, namely the feasible region is below this line, so we can throw away all the points above this line. So now we have a smaller set, and we repeat this process. We compute the center point. We ask the oracle feasible or not. If it's not, we get a separating line. We throw away the points on the wrong side. And we repeat this process until either all the points were thrown out. If all the points were thrown out, that means this undecided LP is not feasible, or one of the queries succeeded and we found a feasible point. So that's the algorithm. Let's think about the performance. So we have n hyperplanes, so it's n to the d vertices. This is, by the way, the algorithm of mass n to 1. So we have n to the d points. If there is a feasible point, one of the points of P must be feasible, clearly. And now what we do is that as long as we have enough points, we compute a center point. As I said, we ask the oracle and we throw away points, and unless we found a feasible point. As far as the number of queries, the key observation is that in every iteration, either we found a feasible point and we are done, or we throw away 1/d fraction roughly of the points. So as such, the number of queries is this expression here, right? We reduce the point by a fraction of 1 minus 1/d if you want in every iteration. So after the iteration, the input size shrink by 2. So after d square log an iteration, we will be done. Okay. That, of course, is as I said earlier, is a pretty bad algorithm because computing the center point exactly is pretty slow. So the question is how to do better. And there is a cutting-based algorithm. So you take the set of lines and you compute the cutting. What is a cutting? It's a partition of the plane into, let's say, R square regions. So R square regions. The regions are going to be triangles, and every region crosses only n/r of the input lines. So this is usually called 1/r cutting. And those cuttings can be computed in nr time. Since r is going to be a constant, it's essentially linear time. So you compute the cutting, and now you look at all the edges of the cutting. Okay. Now, the idea is that we are going to do the undecided LP on each one of the edges. An edge is a one-dimensional entity. And you have to think about it a second, but you can recurse on the dimensions. The oracle still works, everything works if you just go one dimension lower. So you can just solve the problem on this segment. And what does it mean solving the problem on the segment? Either we take all the lines that intersect it and we call recursively on this one dimension lower. Now, if we found a feasible point, we are done because it's a feasible point of the original problem. If, on the other hand, we found that it's infeasible, what it means is that we collected a few constraints such that their intersection is a polygon that does not intersect this edge, right? Now, if you think about this triangle, I can go around the edges of this triangle, right? I go and do this 3 times, call it on the 3 edges of this triangle. If I found a feasible point, I'm done. If not, I know that from the constraints that I collected, the feasible region must not intersect the boundary of the triangle. So it's either inside or outside. If it's inside the triangle, well, call recursively on the triangle. Since the triangle intersects only n/r constraints, we benefited, right? We shrank the problem. Alternatively, the feasible region of the constraint collected is outside this triangle. And in this case, we can just throw the triangle away. This region is not relevant, right? So now what we do, we just do it for all the edges of this cutting, right? For every edge of the cutting, we go and we call recursively to solve this undecided LP. If one of them is feasible, we are done. Otherwise, we collected constraint and we look on the feasible region, and the feasible region must be contained in one of the triangles, and we just call recursively on this triangle with the constraints intersecting the triangle, which is only a constant fraction.
May I interrupt for a second?
Sure.
You mentioned sometime earlier that maybe it's not part of your model to be able to recursion a subset because
right. So the Oracle queries are still on the whole set of constraints, right? So the algorithm go down on the subset of the constraints, but the Oracle returns me a constraint that might not be in my collection. That's fine. It's part of the original set of constraints, right? So if you think about it, for example, I call, let's say, on this segment, right? And it might return me this line, right? Right, telling me the feasible region is here, right? That's great, right? It just tells me this is not feasible and I move on. Okay, so this is where you have to think for a minute to realize that it's okay that the constraint is still, the Oracle still work on the original constraints in the higher dimensions. Okay, yeah. So it's kind of weird, right? Because the algorithm conceptually shrink the number of constraints, but the Oracle doesn't. Okay. So if you do that, this works also in D dimensions. You get this lovely recurrence on the number of queries, and it's not too difficult to show that this is the solution is log D to the n, and the running time is linear, which can be also is not hard to verify. So that's the cutting-based algorithm. And this is kind of the collection of the results we currently have, right? So there is this big discrepancy on the number of queries. We have polynomial number of queries, but the running time is awful. And we have running time, which is okay, but the number of queries is not great, right? It's exponential in the dimensions. And we can have a slight improvement in 2 and 3 dimensions. Okay. So let me mention a few open problems on this undecided LP, because I think there are a lot of things yet to be done here. So, so for larger than 2 dimensions, still constant dimension, can we get log n queries with near linear running time, right? So improve the cutting algorithm, essentially. Another interesting question, can we get LP running time, right? So currently, I hope I'm not lying, the fastest LP solver runs in something like that, 2 to the square root of D times n. This is due to Zwick and some other people, I think. Can we get this running time? Because somehow the natural thing is to try and implement the LP algorithm, but somehow it's not easy because of this exactly this problem of the Oracle working on all the constraints. Other interesting problem in 3 dimensions, can you get log n queries and linear running time? Currently we have this n to the 3/2. And more generally, I think the real question that underlines everything is this question about random sampling. So I'm in higher than 2 dimensions, and I would like to sample a random vertex of the arrangement inside a convex polytope. I give you a convex polytope. This polytope is simple. It's intersection of logarithmic number of constraints. And I would like to sample a vertex to the arrangement inside this polytope. And can I do it efficiently? Efficiently means running time better than n to the d over 2, right? So, and I don't know how to do it even in 3 dimensions, or even in the plane, right? In the plane, I don't know how to get better than linear time sampling from a vertex inside such a polygon. Okay. And the lower bound, I believe that this square log n is a lower bound. Master2Run proves some lower bound, but they prove it on the dual problem, but they prove it for the point set, which is a subset of this n to the d grid. So it's not quite the right lower bound. And I think it would be quite interesting to prove this lower bound for the general setting without assumption on the point set P. Okay, other questions before I move to the next part? How much time do I have, Boris? Just so I don't run over time.
I'm sorry, you already ran out of time, so
Okay.
please rewind. Well, I mean, you can go on until, for another maybe 20, 25 minutes, so 20 minutes probably.
Okay, okay.
That's
Yeah,
fine.
okay. Just making sure. Okay, so we want to label all points again, but so red and blue points. The assumption is that we can cover the point set with K monochromatic disks, red and blue disks. And the queries that I allow you, the Oracle queries are, given a point, give me the closest point that is red and the closest point that is blue of the point. So, and the question is how to do that. And if you think about it, this is really a set cover problem, right? I'm trying to cover the input with red and blue disk. And, if you want to do set cover, then you should do random sampling if you want a fast algorithm, because that's kind of the only thing we have. So we sample the points. And the idea is that you want to find a disk in the sample that is monochromatic, right? All the points in the sample inside it are of the same color, and the disk is heavy. It contains a lot of sample points. And the intuition is that if we find such a disk, we're going to add it to our cover because it's going to cover a lot of points, except that we need to make sure that not only it covers only same color of points in the input, it covers also in the sample, it also covers the same, all the points it covers in the original input are all of the same color. And the sample size we need is K log K. If you think about it a bit for disks. And now we reach kind of the main technical challenge for this, because when I give you a random sample and you're looking for a disk that is monochromatic, this is, for example, such a disk. It's easy to find. In fact, it's very easy to enumerate all possible subsets that you can get by a disk. This is called canonical sets usually. And if you have R sample point, then you're going to have R cubed canonical sets. The problem is that our Oracle requires us to send it a disk, right? We have to send a disk to the Oracle. So at some level, this random sample give us good canonical sets, right? Canonical set that is large, and all the points of it, in it are of the same color. But this canonical set might correspond to an infinite family of disks that contain it, right? Which disk do we need? That's kind of the challenge to find. So the natural thing to do is to try and do some kind of a pursuit evasion algorithm. You send the disk to the Oracle, you ask, is it good? The Oracle says, no, here's a blue point that you're covering. So you said, okay, let me move the disk a bit. And you go again and you ask the Oracle, is this good? And the Oracle says, no, no, no. And the game continues like that, right? And the challenge is to ask, of course, how long do you have to play this game before you converge? Clearly, in the end, you will converge, right? Because in the end, you will get the label of all the points. At that point, you can solve the problem using some brute force. But of course, we would like to make this pursuit sequence as short as possible. And one has to be careful, by the way, because it might be, for example, that you discover a new red point. But since we are covering by several disks, it's not true that this red point necessarily is covered by the same optimal disk, because there might be other blue point that blocks it. So somehow I'm looking for a red heavy disk, but if you tell me that some other points are red that are not in my sample, you're not necessarily helping me, which is very weird. Okay, So, so here's the algorithm. So we are going to, again, we are taking a random sample. We are going to ask the oracle for all the points in the random sample, because we can do nearest neighbor colored query. So we can just ask for the point itself in the sample. What's the color of your nearest neighbor? And now you just go over all the canonical subset of R. And for each subset that is canonical and is heavy, we we try to find a red disk that is consistent with it and doesn't contain any blue points of the original input, and we return the heaviest such disk. Okay, so that's the basic algorithm. It's just a greedy algorithm for set cover with the twist that we need to worry about this red-blue issues. Okay, so computing the heavy disk, how do we do that? So it turns out that the trick is just, as you might expect, you just do lifting for 3D, right? So if you do lifting to 3D, the points become claims, and the constraint is if it's a red point in our situation, a red point becomes an upward constraint, a blue point becomes downward constraint. And now what we want to do, we want to find a feasible point in this undecided LP where the twist is that we are ignoring all the red constraints. So because red point, if you give me a red point, I don't know whether it is or not covered by my disk. So I'm looking only for counterexamples that are blue points. And I can do this, right? Because my oracle allows me to do nearest neighbor blue query, which turned out to be exactly this a blue violating constraint query. So this is just now becoming this undecided LP in 3 dimensions, and we know how to solve it. So that's the algorithm. And the only trick here is in the sample is that we need to use this idea of relative approximation. So I don't know if you're all familiar with that. Relative approximation is something between epsilon net and epsilon approximation. It's something that have the size of an epsilon net, but it approximates every range that have weight bigger than epsilon. It approximates it correctly up to, let's say, a factor of 2 or half, 1 plus minus half. So in our case, you need a sample of size k log k, and then you essentially says, okay, if there is a k disk that cover everything, then there must be a disk of size 1 over k that is monochromatic for the unlabeled points. As such, my relative sample must have a heavy disk that cover 1 over 2k of the sample, fraction of the sample, and they're all the same color. And now by relative approximation, we know that this disk is in fact heavy for the whole point set, right? And again, to find this D, we do this undecided LP. We add it to the cover, we remove all the unlabeled point, and we repeat. So we get this algorithm that if I allow those 2 oracle queries of colored nearest neighbor and sample randomly an uncovered point, I get covered by k log n monochromatic disk, and the running time is polynomial in k and log n. Okay. Okay, so let me mention the same problem for monochromatic triangles. You want to cover a points. Again, you assume that they can be covered by k monochromatic triangles. And again, the 2 oracle queries I'm allowing you is, given a triangle and a color, is there any point in this triangle with a different color? And the other query I require is that, given a partial cover, return me a point that is not covered. So that's the 2 queries. And notice that that's all I need. I don't need the point set even, right? This is kind of cute that I don't know the input. I just have this, right? This input primitives are enough. Okay, so this might look, for example, like this, which is the example you've seen before. So it might be the solution. And now the pursuit thing seems doomed in advance, right? Because it might be that the blue point look like in this drawing and the red point look like the circle on the outside, and there is this tiny opening. And somehow, if you just try to do this pursuit, you would jump around all the time, and you would essentially have to label all the points before you converge. So we need something different. So we need to go back to this idea of canonical points. So, and canonical point set, the canonical set. So to remind you, what is a canonical set? I have a point set, I look on a triangle, and I look on all the points inside the triangle, right? So I look on all the possible subsets of a point set that I can get by intersecting with the triangle. Those family of subsets is the canonical sets defined by the triangles. And the problem, so to bound the number of such sets, what one does some kind of a continuous motion argument, right? To say, okay, I can take the triangle, I can move the edges until I get stuck. Then I move the edge until I get stuck by another point. So I have 2 points, and then you start doing it with the other edge and the other edge. And in the end of this process, you end up with 6 points that, except maybe for the 6 points, all the points inside are the same as in the original triangles. And then you need to specify maybe 6 bits for those points, whether they're inside or not inside. So overall, you get that if you have n points, the number of canonical triangle or canonical subsets is n to the 6, which is fine. The problem for us, what really makes our situation with the Oracle bad, is that these canonical sets are not monotonic, right? This process of moving from an arbitrary triangle into this canonical triangle, this process moves from this triangle to a different triangle, and it's not contained inside the original triangle, right? And this is really bad news for us, because in some sense, all we can do is take random sample and look at the canonical sets, and then for a canonical set, start looking on its triangle, and then start doing this kind of pursuit process. But because of this lack of monotonicity, this seems to be doomed. This, of course, is just intuition, but hopefully you're convinced. So instead of looking on canonical triangles, we're looking on different subsets. We call them self-defined triangles. And the important thing here is that I'm not defining here the subset. I'm defining here the triangle, right? Unlike the previous situation where we defined the subset, which was a canonical subset, here I'm going to define a triangle. And the idea is that you give me some triangle that contains some of the points, right? And I want to find a triangle that is strictly contained inside this triangle and contains a large fraction of the points, right? And I would like to find such a triangle that it's defined in a compact way, such that the number of such triangles, if you give me n points, the number of such triangles is small, some polynomial. So, so it turns out that you can do it. And the trick is to, you look on the convex hull of the points inside the triangle, and you take the vertices that are closest to the edges. By closest, I mean, you look on the normal direction, right? So you take the 3 extreme vertices, and then you take the adjacent vertices on the convex hull, so you get 9 vertices. And you now extend from every one of the 3 original vertices, you extend the line, right? So you get every vertex defined 2 edges adjacent to it. So those 2 edges, you just take the lines to them, and that defines a natural hexagon. This hexagon, it's easy to see that it's contained inside the original triangle by the way I pick those 3 points. So I have this hexagon. This hexagon is contained inside the triangle, and it contains the convex hull. You can triangulate it into 4 triangles. One of those triangles must be heavy, contain 1/4 of the points, right? So we are done, right? We proved that. So the self-defined triangle, the number is going to be n to the 9. right? Because they are defined by 9 points. And there is a self-defined triangle that contains at least 1/4 of the points that the original triangle contains. And now we are back to the games, because now we can just implement the greedy algorithm as before. We take the random sample, we go through all the self-defined triangles, and for each one, we essentially ask, is it monochromatic or not, using the oracle, and we return the heaviest one that we found, which is heavy, using the heavy in the sense of the number of sample point constraint. So we return the heaviest monochromatic one that we found, we add it to the cover, and we remove all the points that it covers, or mark them as labeled, and we repeat this process. So we get again this algorithm that does polynomial k and log n queries and label all the points, or if you want, cover all the points by relatively small number of triangles. Okay, so we had reached the end. So there are a lot of interesting open problems, I think. I think the most interesting thing for me is to find under algorithm this implicit input model for geometric settings. I think that there is a chance to find a lot of interesting stuff there. Let's see if the camera works now. I guess not. So that's one thing. And other interesting stuff is, for the undecided LP, can one do better in lower dimensions, and also prove a lower bound the number of queries. That's it. Thank you very much for your patience.